All right, so on in-class problem number 3. Units are going to be important. They help us kind of keep track of what's going on in our problem. So when number 3 talks about a balloon that is filled with helium, and the balloon has a mass of 0.008 kilograms. What is kilograms telling us? Now there's also this word right in front of it that kind of gives it away as well. But kilograms is a measure of mass, right? Not F a G, not a weight, not a force, it's mass. It's a kilogram, okay? Now it also, like I said right before, it said a mass of. And it says is filled with 0.03 meters cubed. Meters cubed is a measure of volume. What if it's meters squared? It'd be, no, meters per second, or meters per second squared would be a speed or acceleration, but if it was just meters squared, then it'd be, think math class here. Yeah, it'd be area, okay? This is meters cubed, so it's talking about meters cubed or volume of helium. What is the tension in the string? So we're going to start with a balloon that has a string tied on it. Now there's a part there that talks about Russell from the movie Up. We're not ready to talk about Russell yet. So there's tension in this string. If I were to cut this string, which way does this helium balloon go? It's going to go up. So which way is the string pulling? Down. Right? So the tension in this string is down, and that's what we're trying to solve for. Helium balloons float. Let me rephrase it. Most helium balloons float. Why would a helium balloon not float? What's too heavy? Okay, I see what you're saying. It wouldn't fly away if the thing attached to the string was too heavy. Is that what you're saying? Okay, that's not what I meant, but that is a very true statement, right? As long as we have something heavy enough attached to that string, that balloon is not going to fly away. Well, what would prevent a helium balloon from lifting up, even floating at all? The weight of? Again, that's kind of that string thing, right? So that hold it down. But what if the balloon, I don't have a balloon. I have a balloon, and that balloon is just no string, it's just sitting right here. It'd have to be a really heavy balloon, whatever that balloon thing is, which would be a terrible balloon if it was so heavy that it wouldn't allow it to lift. But the idea is it could. In chemistry class, you filled plastic bags with different gases, and you found the masses of all those. Those bags didn't fly away. One, they had a rubber stopper and some of the other things. But if you were just to fill that thing with helium, it wouldn't be enough to float away because the bag itself was too heavy. Okay? So just something to keep in mind. That balloon, the balloon itself has a mass. Okay? Is helium the only thing that could make a balloon float? Could we fill a balloon with something besides helium and make it float? Are there any other gases that we could put in a balloon that are buoyant enough that it would float? Anybody know what a blimp is filled with? Yeah.
Hydrogen?
We could fill it with hydrogen. Yeah. Okay. The blimp, like the Goodyear blimp, not. It's helium. Have we ever historically filled balloons with hydrogen? Yes. Yeah, there was that one time that they filled a blimp full of hydrogen, and it kind of burned and blew up. The Hindenburg, I think it was Hindenburg, which was a Zeppelin?
Yeah.
Is that the right? It was Zeppelin. Zeppelin, right? It was a German blimp I think it was during World War II, actually. And it was parked in New York, which was meant to be like a luxury airline cruise kind of thing. So, hydrogen does work. Not the best choice, because what else is true about hydrogen gas? It's combustible, it burns, right? So we can burn, there's hydrogen cars that can burn hydrogen gas, we can combust hydrogen, so not the best choice to build out of, but it is light enough that it could float, and it does float. But this one happens to be filled with helium. So we already identified that this balloon is filled with helium, and the volume of this helium in the balloon we identified by the units was 0.03 cubic meters. Okay, so we have a balloon that is filled with 0.03 cubic meters of helium. So if we're going to try to figure out how much tension is in the string, eventually we're going to do a Newton's second law. We're going to add our ups, we're going to subtract our downs, we're going to set it equal m times a, we're going to solve for f of t. That's going to be like the last step. Before we can build Newton's second law, we first have to figure out what are the other forces acting on this helium balloon. The balloon's going to float. Why is it going to float? Because there's a title is worksheet. And there's a buoyant force. Now, we've really only talked about buoyant forces in terms of calculations for when something is immersed in water, when it's floating in water, when it's sitting in water. And I've mentioned this multiple times, but anytime an object is immersed in a fluid, air is a fluid, there's a buoyant force. So because of the difference in the densities between hydrogen and helium, there is a buoyant force that is going to be significant, and it's something we're going to consider. What else do we have for forces? I'll give you a clue. We talked about the mass, and mass is a good indicator that there's a gravitational force. Now, specifically, what is that the mass of? It's the mass of the balloon. So when we talk about Fg, this is the Fg of the balloon. Now, when we talk about the Fg, or the weight of the balloon, what I'm talking about is the latex part of the balloon. Or it could be vinyl, or it could be mylar. Insert the material of the balloon. Typically, they're latex. So we're talking about the actual weight of the balloon. So when we talk about the weight of a balloon, well, F of g is m times g. So if I want to take F of g, if I want to fill that value in of the balloon, we take the mass of the balloon times our gravitational acceleration, and our Fg of the balloon, and I'm just abbreviating balloon, is going to be 0.008 times 9.8 for Fg of our balloon to be 20? That's 20. To give us F of g of 0.0784. Okay. So that number, newtons, is the weight of the balloon. There's a buoyant force. And if we kind of want to keep with that trend of let's fill in as many numbers in my free body diagram first, because then when we build Newton's second law, we just got to plug numbers in. That's fine. So when we talk about our buoyant force equation is equal to the density that's being displaced times the volume that's being displaced times g. Now I'm writing it like this because I want to just kind of draw emphasis to it. Some of you might just jump right to the next line. But it says dis as in it's displaced. It's the density of what's being displaced. It's the density of what's getting pushed out of the way. It's the volume that's being displaced. It's how much of that stuff is getting pushed out of the way. So in this situation, when I fill a balloon with helium, that was my helium tank, and my balloon is now this big, what did that balloon push out of the way when I filled it with helium? Pushed air out of the way, right. So what was displaced? It was air. So this is going to be the density of air. The helium pushed air out of the way. Times the volume that's being displaced. Now, let's just pretend for a second that this is my helium balloon. Oh, look, I filled a helium balloon that big. How much air did this thing push out of the way when I filled it? the same, this much, right? Whatever this volume is, it displaced its same thing. Archimedes, the whole bathtub eureka guy, when he climbed in the bathtub, the water level went up and overflowed because he displaced a certain amount of water. He displaced his volume of water. So when we've talked about these objects, like if I put a block completely underwater, it's completely immersed, therefore it's displaced this entire volume. If it's only partially underwater, then only the part underneath the water has displaced water. The fluid we're talking about here is air, and if I have a helium balloon completely surrounded by air, how much air was displaced? Well, it's equal to the volume of the object. So in this case, the volume of air that was displaced, how much air got displaced, is equal to the volume of the helium balloon itself. Plus a little tiny bit. Now why is it plus a little tiny bit? If I put 0.03 cubic meters of helium in my balloon, we actually have a slightly more air is displaced than 0.03 because where does my helium stop? Right there, right? And where does my air start? Right there. Does that balloon take up some space? A little tiny bit, right? So it's negligible, but realize that that balloon does take up a little tiny space. So it's a fair assumption, it's a fair conclusion that we can say the total volume displaced is pretty gosh darn close to the volume of the helium that we put in the balloon. It's technically a tiny bit more, but not enough to deal with, times our gravitational acceleration. So we got to make sure we multiply by 19. So given in the problem was the density of air, so F of B is equal to 1.29 times the total volume of the helium, which is 0.03 meters cubed, times 9.8. And then we take 1.29 times 0.03 times 9.8 for our buoyant force, our F of B, to be 0.37926 newtons. I'm going to keep as many decimals as I can along the way. Okay, so then up here, I can say, well, this is 0.37926. And most people say, I'm done. I got all my forces identified. Let's do that Newton's second law thing where I add my upsets, subtract my downs, etc. equal to m times a. We're not quite there yet. And there's one more force that's often mistaken. Anybody want to tell me what it is? Or? And a lot of times people say, well, it doesn't really matter, it's not that significant. But does helium take up space? Is helium made up of atoms?
Yes.
Does helium have mass?
Yes.
So does helium have a weight?
Yes.
It does, right? So anything that has mass, which mass is anything that is made up of matter and takes up space, check, 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 right? We have all those things. Because of that, we also then have to consider the F of G of the helium itself in the balloon. Now you might say, it's got to weigh next to nothing. It's lighter than air. It's something, and it's something that we got to take into consideration. It's the reason why a balloon filled with air doesn't float. One of the reasons. It's the density, this difference in density thing too. But if I fill a balloon this big of helium and it floats and I fill it the exact same size full of air, it doesn't float. The balloon is the exact same, the volume is the exact same, my buoyant force is the exact same because the volume is the same. The difference is the weight of the air in it isn't enough to allow it to float. So what we have to calculate is this mass of our helium, which in order to do that mass of helium calculation, it's the same kind of calculation we've done a bunch of times. If you knew the density of an object, and if you knew the volume of that object, you can then calculate the mass of that object. And the density of helium is 0.179, which is considerably less than air, which is 1.29. It's given in the problem, just for the record at the very end. Divided by the mass of helium times the volume of helium, which is 0.03, which then we can calculate the mass of that helium. So if we take 0.179 times 0.03, we get a mass of 0.00537 kilograms. So my mass is 0.00537 kilograms. The reason we really are concerned about the mass is not necessarily because of the mass part, but in my free body diagram, it's what we can use to calculate weight. So when we multiply that by 9.8, we get that for weight. Now if you compare the weight of the balloon to the weight of the helium in the balloon, they're kind of close. The weight of the balloon was 0.07, the weight of the helium was 0.05. They're pretty close, so it's something that definitely needs to be considered. Now, we are at the free body diagram being completed. Now we're going to use Newton's second law. Sum of all my forces is equal to F net, which is equal to mass times acceleration. The balloon is being held in place, it's not accelerating, the tension is equal to, or my forces in the y direction are balanced. Acceleration is 0 because my velocity is constant. We're holding on to that balloon. Newton's second law says I add all of my ups. I only have one. It's a buoyant. I add my ups, plural, I only have one in this case, and I subtract my downs, which means all of my downs. I'm going to subtract my F of G of the balloon. I'm going to subtract the FG of the helium. I'm going to subtract the FT, tension in the string, and I can set that equal to 0. I add my ups, there was 1. I subtract my downs, there's 3 downs. So I need to subtract all 3. Because I had kind of gone through and filled in, I calculated these numbers along the way on my free body diagram. I'm at the point where I can just plug numbers in. My buoyant force, 0.37926, minus the FG of the balloon of 0.0784, minus the helium, FG of the helium, which is 0.052626. Oh, I forgot. I often like to get FT to the other side, and that in the blue, the stuff I wrote in blue, and I get lazy sometimes. So if this is a minus FT, how do I get FT to the other side? Well, I add it, and if I add FT to 0, I end up getting FT. So I think I've showed you this before. If this is a minus, I sometimes say, well, if I'm going to add that, that becomes an equals, and I just kind of, right? I added it to the other side, now it equals. It's FG of helium equals FT. So then this equals so if I take my 0.37 number with all of the digits, and I've subtracted from my 0.07 number with all my digits, and I subtracted from my 0.05 number with all of my digits, I end up getting an F of t. I get an F of t that's equal to 0.248. 2 blah, 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 newtons. So my tension in that string is 0.248. I'm going to store that because we're going to need it a little bit. The force that often gets overlooked in a balloon problem like this is the weight of the helium in the balloon. A lot of times people just like, whatever, it's really small, it doesn't really matter. It is significant enough that we need to make sure we consider it. Okay. There's one more part to this balloon problem. And the next part is, how many balloons would it take to lift Russell from the 8-year-old from the movie bell? So let's just change my F of t number for a second. Let's just pretend that this is 1 Newton. Okay? Let's pretend for number's sake, and purposes of this kind of conversation only, let's say Russell had a weight of 10 newtons. He doesn't. Let's just pretend for a second he does. If he stands on a bathroom scale, and it measured in newtons, and he weighs 10, the scale is going to say 10 newtons. You okay with that statement? Russell weighs 10, scale says 10. If I give him a balloon that the tension in that string is 1 Newton, if I hand Russell a balloon, a helium balloon, is that balloon going to lift upwards on Russell, push downwards on Russell, or have zero effect on Russell's scale weight? Again, made up number, he's 10, the balloon's 1. Is the scale going to read the same, greater, or less than without a balloon? It's a helium balloon, remember? So when we talk about Russell, there's my balloon, there's Russell. I think he had a propeller in his hat, right? Okay, so if Russell's standing on the ground, and if, for a second, we say Russell's at an FG, I'm going to erase this number in just a second, of 10 newtons, because it's not 10. What does that balloon do to Russell? Is that balloon lifting up on Russell, pushing down on Russell, or have no effect on Russell? Tension here in the string is down. But if I cut that string, which way is the tension for Russell? Well, in this case, the tension in that string is upwards. Made up number, I'm going to erase this in 1 second. If each balloon I give him is lifting up on him at 1 Newton, if he weighs 10 and I give him 1, the scale is going to read 9. If I give him a second balloon, it's going to read 8. Another one, 7. Okay? And eventually we get to a point where Russell, it lifts him up. Movie up. It lifts him up into the air if we give him enough balloons. Okay? So the question here is, how many would it take? So going back to the problem, it says Russell has a mass of 30 kilograms. 30 kilograms times 9.8 is going to be Russell's F of G. Russell's weight, if he was 30 kilograms, is 294. Not 10, I just made that number up for purposes of trying to talk you through some things. Russell's weight would be 294 newtons. I question a little bit if Russell is really only 30 kilograms, which would be right around 60-some pounds. I feel like Russell was more than 60-some pounds, but whatever, we'll go with it. Okay? The tension that we calculated over here is the tension that is lifting upwards on Russell. Now Newton's third law, here my tension was down. This was the forces on the balloon, but we're not talking about the forces on the balloon anymore. Now we're talking about what are the forces on Russell. But Newton's third law says, well, the string is pulling down on the balloon, but in the equal and opposite forces, the balloon is pulling up on Russell. So this is Newton's second law, sum of my forces is equal to F net, which is equal to mass times acceleration. And what we're trying to do is we're trying to figure out what is like that minimum number of balloons before Russell starts to move, before he accelerates. So we're still saying his acceleration is 0 because his velocity is constant. He hasn't started to move yet. So Newton's second law says I have to add my ups. Now I'm going to leave a little space here. I'm going to add my ups, and my ups with the space left in between is equal to, is an F of t. I'm going to subtract my downs, which is equal to 0. Now, if I give Russell one balloon, it's going to lift upwards on him at 2.248. If I give him two balloons, it's going to be twice that much. If I give him three balloons, it's going to be 3 times that, and so on and so on and so on. So what we're trying to figure out is how many, or X number of balloons, where X represents the number of balloons it'll take to lift Russell up. And that's what we're solving. Same kind of lazy math thing that I did before. This is a minus, I want to move it to the other side. There, I moved it to the other side. So X times F of t equals F of g. And I can say X is equal to 0.248, which is equal to 294. So X is equal to the number of balloons that it will take to lift him upwards. Now I'm going to use my full 0.248234 number, and X is equal to 1,184.37 balloons. Now, that number of balloons is the number of balloons it'll take him to not move, to not change his velocity, to not accelerate. According to the scale, he weighs nothing. He's on that verge of being lifted up, but he's not being lifted up quite yet. So if I were to round, and I want to know how many balloons would it take to lift Russell, do I follow the rules of rounding, or do I just got to go to the next highest number? If I round down, well, then he's not going to be floating. So the idea in this situation is we got to go to the next highest number. The number of balloons it'll take to lift Russell up is 1,185 balloons. That's like the minimum whole number of balloons that it'll take. Then he will start to accelerate upward, and he will start to move up. Okay, so that is similar to your problem on your homework sheet called number 5. So by Sunday, you should have enough background to finish that entire homework sheet. With the rest of class today, about 15 minutes, I have a progress quiz. And the progress quiz that I have for you is a buoyancy, and it's one of those like how far underneath the water is it. And there's a lot of parts to this problem, and my idea when I wrote this was trying to kind of mimic my thought process. So in this problem, it gives you some information, gives you some dimensions about a block. Part A says draw a free body diagram. Number 2, what is the mass of the block? Because in order to fill out a free body diagram, you're going to have to know F of g, and I'm not nice enough to give you the mass, so you're going to have to figure out the mass. Then, use Newton's second law to build an equation. Then, what is the object being displaced? Because in that equation, it's the density being displaced. I have to identify what's being displaced first, so I know what to use. Then what is the value of that? What are the dimensions that are underneath the water in terms of like a variable? And then finally, how far under the block? The reason I did an A through G, again, is to try to break it down sequentially, and this is kind of how I solve these problems when I go through and do them. If you say, boy, that's really dumb, why would you do it that way? Don't. I don't really care. If you wanna go right to part G and figure out how far underneath the block this is, go for it. Again, this is meant to kind of guide you in terms of like a thought process. But if you say, hey, I'm pretty good with these, I know how to do them, go right to problem part G and solve for it, because that's ultimately what I'm looking for. So the answers to this are posted, they're sitting on that lab table back there. Once you have this complete, then I'm gonna ask that you finish that last homework problem, or finish working on that, or continue to work on that homework problem. The homework sheet called Buoyancy is due in Canvas on Sunday. And then we will introduce the information to do the lab tomorrow, but we'll do the lab actually when we return on Monday. So I know I'd originally said lab on Friday, but it's gonna be on Monday now instead. So let me know what I can help you with. Again, answers are posted back there.